Welcome everyone. Today we'll learn trans effect, the theory of trans effect, some examples, mechanisms, and the application of it. So prior to start the trans effect, first we have to understand what is basically trans effect mean. See that the principle of trans effect actually was first established by the scientist Chernyv in the year 1926 when he observed on the substitution reactions at platinum-2. He observed that certain ligands facilitate the substitution of ligands that is in a position trans to them. Basically, it is in a square panel arrangement where you can see that each ligand actually is trans to another ligand. Basically, there are 4 ligands, but each ligand is trans to another ligand. And these trans effect actually, due to this trans effect, you can arrange different ligands in a series according to its ability to show the trans effect. Whatever we have shown in this slide, that is from weak trans effect or the weak field trans effect to the strong trans effect. So this is basically the trans effect. Like for a square planar type of complex, certain ligands facilitate the substitution of ligands that is in a trans position to them, and basically this effect can be categorized as a series of these ligands according to its ability to show the trans effect. Like whatever we have shown in this slide, that is the series of these trans effect or the order of trans affecting ligands from weak to strong field. Now we have to learn why does trans effect occur. So there are basically 2 theories behind these. One is the ground state effect and another one is the transition state effect, right? So the ground state effect can be recalled or can be considered as the sigma effect also, whereas the transition effect can be considered or can be recalled as the pi effect also. First of all, we will learn the ground state effect or the sigma effect. So this is basically the first theory for the trans effect. So for this theory, suppose prior to start this theory, suppose we have a complex, that is we have a complex which is basically pt, suppose pt x4 2 minus. So basically this is symmetric. So for each x ligand there is another ligand which is trans to it, but both are actually same ligands, right? So due to this symmetric nature of pt x4 2 minus, it will not show any kind of trans effect. So basically whatever will be the trans directing order of x, that would be same, right? So this x, if I am selecting this x, so this x is having the same trans order or trans affecting order like this x. So basically this is not going to show any kind of trans effect. Suppose in this complex, any one of these ligands, any one of these x ligands has been replaced by one ligand, that is L, or suppose a ligand A. One of the x ligands among 4 have been replaced by A, like so. Therefore the complex structure will be pt x x, now one A and another x, all over just say for the same like 2 minus. Okay, now consider that A is a strongly polarizing ligands, or suppose A is more polarizable even than the X. Okay, so A is highly polarizing or strongly polarizing ligands. So if A is highly polarizing ligands, so it will pull electron density. It will pull electron densities from the central metal atom. Wherever we have taken the example like platinum 2 plus, so if the central metal is platinum 2 plus, so the A ion or the A ligand, not A ion, actually the A ligand will pull the electron density towards itself or towards themselves from platinum 2 plus ion, right? So therefore the primary charge on metal ion actually induces an dipole on X, or induces an dipole on the ligand, which is actually trans to A, right? So therefore basically the negative charge would be generated like we have shown here, that due to this primary charge on platinum 2, it has induced an dipole over here, that is a gain of negative charge, and due to this negative charge actually the anion, actually this is the X minus, whichever we have already told, that this anion will comes into the repulsion, right? Repulsion with the platinum 2 plus due to this induced negative charge, because the anion is already negative charge, and due to this induced dipole the negative charge has been established, so therefore the repulsion occurs, and due to this repulsion the platinum X bond or the platinum chlorine bond, or you can say the bond between the central metal atom and ligand, which is actually trans to A, that is which is actually trans to the attacking ligand, would be weakened due to this repulsion between the negative charges, and therefore X minus will be released very easily, or you can say in this example the chloride is releasing very easily. So overall the ground state effect or the sigma effect can be summarized as follows, like when a strong polarizing ligand is attacking, for example a symmetric complex like PTX42 minus, so one of the X ligand has been replaced by the L ligand. Suppose L is very highly polarizing or strongly polarizing ligands, then it would pull the electron density towards itself from the central metal atom or the central metal ion. When it will pull the electron density towards itself, then the primary charge on the metal ion actually induces an dipole on the ligand, which is actually trans to A, or which is actually opposite to A, and therefore the negative charge has been generated over the platinum, or actually the negative charge has been induced due to the central metal atom, and therefore the negative charge between these, due to this induced negative charge, there would be the repulsion between these X, or between the ligands and central metal atom, the ligands which is actually trans to the attacking ligand. So therefore the trans ligand actually being replaced due to the repulsion. Okay, like in this example the platinum 2 cation actually induces a dipole in the polarizable trans-directing ligand A, and therefore the induced dipole in ligand A induces a dipole in the polarizable platinum 2 cation. The chloride ion trans to A is more easily released due to the extra repulsive forces between its negative charge and the induced dipole of the platinum 2 cation. Okay, so now again we are explaining this thing. Again we are taking another example, or you can say that broadly actually we are explaining. Say for this example, it is also a symmetric type of complex or a symmetric complex, that is central atom is M or the central metal atom is M, whereas 4 ligands are there. The overall complex is symmetric because each ligand is same, like L, right, whichever we have been considered here. But suppose that one of the L has been replaced by other ligand like T, and T is supposed to be more polarizable, then it would draw the electron density, more electron density towards itself, and therefore due to the primary charge of the metal ion, due to the primary charge on the metal ion, it induces a dipole on L, right, or it induces a dipole on T actually. It induces a dipole on T. These may in turn induce a net polarization on the metal in a manner that it will repel negative charge on a ligand X trans to L, or as a simple manner you can understand like these, that whenever this is like platinum 2 plus, say for L, say it is X, it is X, it is X. Okay, so say that if the platinum 2 plus is like this, and say this is the X and this is the A, which is actually more polarizable. So when actually this is the central metal. Okay, so this is the central metal. Suppose M and all over charge is N plus. So when actually A being more polarizable, it is drawing more electron density, and therefore A would induce a dipole. A would induce a dipole where actually A would induce over M like this, that it is having the minus charge. So therefore here plus charge would begin because it is inducing a dipole in such a manner that a opposite charge would be established on the side of X, right? Or induce a net polarization on the metal in a manner that it that will repel negative charge on a ligand X trans to A. So because this is already having the negative charge, it is a negative ligand. So therefore due to this repulsion between these negative charges, the release of X minus would be facilitated. Okay, so this is basically the ground state effect or the sigma effect, which is the first theory of trans effect. Now when we are considering this theory, then basically we can tell that the more polarizable a ligand, the more will be its transdirecting order, right? And this can be consistent with the observed trends also. Like the trans effect order actually follows like H minus greater than I minus greater than actually I think it is Br minus and greater than Cl minus. Also actually ammonia is showing trans effect more than water. Why? Because that more polarizable will be the ligand and it will show or it will have a more transdirecting order. Like the hydride, it is more polarizable than iodide, whereas iodide is more polarizable than bromide followed by chloride. Therefore the transdirecting order would be the same like ammonia, same like between ammonia and water, as ammonia is actually more polarizable than water and therefore is having the same transdirecting order also. That is, ammonia is having more transdirecting power than water. Okay, so we are moving to our next theory, that is basically the transition state effect, or you can say the pi effect. See that whenever you are considering the transition state effect, it is basically the pi effect, means the sigma consideration is sigma thing is, or the sigma effect is not being considered here. So here actually we are considering that whenever the substitution reaction is occurring, it is going through a transition state, and the transition state is actually a 5 coordinate transition state, or you can say an intermediate also. Now in this case, first of all, the transition state is being stabilized, right? That is a TBP, trigonal bipyramidal transition state, is being stabilized. But how is it being stabilized? Because say for example, when a square planar complex, say for example I am taking mx board, when it is being attacked with another ligand, say for X, so it is forming a transition state like a TBP type of transition state, where the L would be, that is the attacking ligand, where the L would be the attacking ligand in the plane. Why? Because the ligand is a pi acceptor ligand. Due to this pi acceptor character, actually the transition state is being stabilized because it is enhancing the pi bond character or the partial double bond character, and due to this nature actually it is stabilizing the transition state. But why or how actually it would stabilize the transition state, or for what arrangement actually it would stabilize the transition state? For that case actually the ligands should be in the equatorial position, because we already know that metal to ligand pi back bonding actually is being enhanced when they are in same plane, or they are in equatorial position. So rather than the axial position, L or the attacking ligand, if it is a pi acceptor, it would prefer to be in the equatorial one rather than the axial one. So therefore the stability would be increased. But if L is being exchanged with the X ligand, or L is placed in the axial position, the stability would not be increased. Why? Because there would be less metal to ligand pi bonding. But when it would be in the plane, when the L would be, or when the attacking ligand would be in the equatorial plane, due to the metal to ligand pi bonding nature, the stability of the all over transition state would be increased, and hence the substitution actually occurring. Like whatever we have here shown in the left hand side of our slide, that is the trigonal bipyramidal transition state, or you can say the intermediate of this mechanism for this transition state effect or the pi effect. And the right hand side picture, it is actually telling that how the pi back bonding actually occurs from metal to ligand. Like in this case actually we have shown that from platinum to ligand, how the pi back bonding is happening. Okay, so now in the next slide actually we will discuss in more depth to these we will discuss deeply the transition state effect or the pi effect. Okay, so see that in this case we are trying to elaborate the mechanism. See that this is a square planar complex. For example, this is a square planar complex, that is M, L2 and X2. Suppose the attacking ligand is Y. Okay. So now Y will be attacked. For example, we have taken here the two arrangements, because when a ligand is attacking a square planar complex, basically two arrangements are possible or two pathways are possible. How? Because when Y is attacking, suppose there are two X ligands, and we are taking an example that X are the leaving groups, or X would be replaced by the Y. Then there are two X. So therefore there could be two pathways also. So now here are three rules actually. The rules are like, when Y is attacking this square planar complex, now 5 coordinate intermediate would be formed. Now in this 5 coordinate intermediate, the attacking ligand, in this case like we have mentioned as Y, the leaving ligand, means in the two pathways actually, either this X or this X would be the leaving group. So therefore first one would be the attacking ligand, the leaving ligand, and the ligand originally trans to the leaving group, that is one of the L, either L2 or L1. So the attacking ligand, the leaving ligand, and the ligand originally trans to the leaving group would be in the trigonal plane when we will draw the transition state. So in the transition state, the three ligands, that is the attacking ligand, the ligand which is leaving, and the ligand which is actually opposite to the leaving group, would be in the equatorial plane or the trigonal plane. So therefore the axial planes or the axial positions would be occupied by the two groups that were originally cis to the leaving group. Suppose if this X would be the leaving group, then the axial position would be occupied by this L2 and this X. Or suppose if this X would be the leaving group, then the axial position would be occupied either by this X or by this X and this L1. Okay. So from the relative number of d pi orbitals available to a ligand at axial and equatorial positions in a trigonal bipyramid, it is known to us that metal to ligand pi bonding is, or pi back bonding is most efficient when a pi acceptor ligand actually occupies the equatorial position rather than the axial position. Okay. whatever actually we have mentioned in the earlier slide also, or in the last slide also. So basically in this case we are now try to discuss the mechanistic pathway. Suppose this Y is actually attacking this square planar complex, and in our first case we are taking an example. Suppose this X will be the leaving group. Okay, so now how will you draw the transition state? See, for example, for a TBP structure there would be one axial group and there are three equatorial planes, right? So which ligands will occupy the equatorial planes and which ligands will be placed at the axial position? So now the central atom would be M, right? And now Y is attacking, so definitely Y would be in the equatorial plane, right? So suppose we are taking Y here as the equatorial plane. So now when Y is attacking, suppose this X is actually leaving. So now if this X actually leaving, then definitely this X would be in the equatorial plane, whatever we have already mentioned as per the rule. So now this X would be in the equatorial plane and the trans of this X is actually L1. So this L1 would be in the equatorial plane. So whatever will be in the axial plane, so actually the axial plane, in the axial plane, the cis groups which are actually to the leaving X would be in the axial plane, right? So L2 and X would be in the axial plane, like for LX and L2. See, just try to elucidate these with this diagram, that YX and L1 in the equatorial plane and L2 and X in the axial plane. Suppose this X is the, now in the next case we are taking an example that this X would be the leaving group. Now this X, if this X would be the leaving group, how will you draw the transition state? So what are C's to this X? C's to this X are this L1 and X. So this L1 and X would be actually in axial position, and what will be the in the equatorial position? Equatorial position would be L2, Y and X. Okay, so this would be in the equatorial position and there would be the central metal atom. So now when the X will be removed, you can just draw the simple square planar structure that the X and Y would be like this. So X and Y would be just in cis position and L1 and L2 would be just in the opposite direction. Like in these scales also, L1 and L2 would be in the same scale, or in the would be just adjacent to each other, you can say, and these XY would be also adjacent to each other or in the cis position. So it is easy to draw the second step actually, right? So just in this slide we have tried to establish the mechanism and the mechanistic pathway also, that when the Y is actually attacking, so basically there would be two pathways, and how would you draw the pathways and through these transition state we have already discussed in this slide. But prior to that, for this mechanism you have to remember the most important thing, that is for the metal to ligand pi bonding, the attacking ligand should be in the equatorial plane definitely, and whenever the attacking whenever the ligand is actually attacking to a square planar complex, definitely the attacking ligand, the ligand which is actually the ligand actually which is leaving, and the ligand which is actually trans to the leaving group, these three ligands will be in the equatorial plane, and the two ligands which were basically cis to the leaving group would be in the axial position. I am just summarizing once again, that is the attacking ligand, the leaving ligand, and the ligand which is actually trans to the leaving ligand would be in the equatorial position. The two ligands which were basically cis to the leaving group will be in the axial position. So through this actually you can draw the transition state, you can draw the pathways of the transition, pathways of the mechanism, and through this you can just try to estimate or try to evaluate or try to show the different products. Okay, so far so good. So see that here actually two pathways are being favored, right? But in the ground state effect or the sigma effect, we have already seen that only one product is being formed or only one pathway is actually applicable, and therefore it is giving only one product. But here actually two pathways are favored, and therefore we are getting at least two products. But then we have to determine the stability difference, right? Suppose if between L1 and L2, whenever we are considering, suppose that if we are differentiating between these L1 and L2, say for example, L1 is a better pi acceptor. L1 is a better pi acceptor. Suppose, so then definitely L1 would prefer the equatorial position rather than being in the axial position, right? Because in the equatorial position it would get the strong pi acceptance character, or it would get a strong metal to ligand pi bonding due to its strong pi acceptance character. But in the axial position it will lack that favor, right? Because in the axial position it would not get that type of metal to ligand pi bonding, whereas in the equatorial position actually it will get that type of metal to ligand pi bonding. Therefore actually L1 ligand would prefer to be in the equatorial position rather than in the axial position if it is a strong pi accepting ligand, right? So now when L1 would be a strong pi acceptor, now in between these two stages or in between these two pathways actually in which L1 is in the axial position, that one will be more preferred than the other. So now in between these two cases, here actually L1 is placed in the equatorial position, whereas here L1 is placed in the axial position. So definitely it would be less favored if we are considering L1 as a better pi accepting ligand or better pi acceptor. Then therefore this mechanistic pathway would be more preferred, and we will definitely get this product, that is one type of square planar complex with the help of this first mechanism only. So that will be the actually major product, and in this pathway will actually not be preferred or will not be favored actually, and we are not getting this product, that is the second product. We are not getting this second product, we are getting only this first product. So far so good. Actually we have got already the knowledge of this trans effect, that is what is trans effect, the trans effect order, and the theory of trans effect. That is, there are basically two theories. One is the ground state effect, that is a sigma effect. Another one is the transition state effect, that is the pi effect. And the basic mechanism of this type of theory, that is in the sigma effect, the basic theory is the polarizability theory, whereas in the transition state effect, or there is basically the theory of pi acceptance, or in the transition state, that is the 5 coordinate 3bp type of transition state. Here we are actually considering the metal to ligand pi bonding basically. Okay, so now in the series nickel to palladium to platinum to, only platinum 2 shows significant trans effect. Okay, but why platinum 2 is showing significant trans effect rather than nickel 2, whereas palladium 2 is basically showing a very less trans effect? They are showing, but they are showing very less trans effect. Why? Because the separation between the 5d and 6p orbitals is sufficiently small to give rise to dp hybrid orbitals. You should mention that to give rise to dp hybrid orbitals, which is actually suitable for the pi bonding with the ligands, or you can say that the metal to ligand pi bonding with in TBB type of intermediate. Now see that whenever you are moving from along group from top to bottom, then definitely the size of the atom is being increased. When the size of atom is being increased, they are more diffused. When they are being more diffused, then definitely the inter-level energy gap would be small. Say for example, we are considering that the energy gap between these 1s and 2s like this, then definitely whenever we are going to from top to bottom, when the size of these atom actually is increased, then you can say this, if this would be the 5d, then this would be the 6s, then this can be the 6p. So definitely these difference in energy between 5d and 6p would be sufficiently small, and it would rise to give a hybrid orbital like dp, which is basically suitable for this type of metal to ligand pi bonding in this type of TBP intermediate, where actually the transition state is being stabilized through this type of pi back donation character. So therefore basically platinum 2 is showing this type of trans effect more than nickel 2 or palladium 2. Okay, we want to mention another difference or another example between platinum 2 and platinum 4. Okay, we just want to mention this thing also, that which metal atom or which metal ion actually is more prone to show the trans effect. See, for example, this is platinum 2 and this is platinum 4. Now the overall positive charge density is very high in platinum plus 4 rather than in platinum plus 2. So basically see that in the sigma effect, whatever we have actually learned, that when the central metal atom is being attached with symmetric ligands, and among these symmetric ligands someone is being replaced by another ligand, suppose L, and now if the L ligand is more polarizing than X, suppose this L ligand if is more polarizing than X, then definitely actually it would pull the electron density from M. So see that M should be highly polarizable, right? M should be highly polarizable. So highly polarizable means that it should have a less charge and comparatively large radius, right? See, I am summarizing again that in the first theory whatever we have learned, that when M is being attached with 4 symmetric ligands, and among these 4 ligands, if one of the ligand is being replaced by a ligand L, and suppose L is more polarizing, then it would give the trans effect, or it would show the trans effect. But when L would be more polarizing, then it would actually try to pull the electron density towards itself. Then definitely if L is more polarizing, then this M or the central metal atom should be highly polarizable, otherwise the it would not show the trans effect, because when L is actually pull the electron density towards itself, then due to this actually M should be more polarizable, and that's why actually it would induce and dipole towards L, and due to this actually an opposite charge is being generated as per the side which is actually opposite to L, and therefore due to this negative charge, gaining negative charge at the site of X, the repulsion would occur with this X, and X would be easily released, right? So therefore this is how the trans effect is being occurred in this sigma type of complex. But whatever actually important in this thing, that when L is actually strongly polarizing, in that case M should be highly polarizable in nature. If M is not highly polarizable in nature, then it would definitely not show a strong trans effect. But between platinum 2 and platinum 4, platinum 2 is actually highly polarizable. Why? Because the charge is comparatively less and size is comparatively large than the case whatever is in the case in platinum 4, because the charge is comparatively higher, wherever the radii of platinum 4 would be less than platinum 2. So therefore it would be less polarizable, and it would not prone to show any kind of trans effect, or it would show very less trans effect rather than platinum 2, where it would show a very high trans effect. So I am just summarizing once again that among the group or in the group nickel 2, palladium 2 and platinum 2, only platinum 2 will show a very significant trans effect. Why? Because in case of platinum 2, its size is being increased when we are going from top to bottom along the group, and therefore due to this increase of size, or you can say that due to this decrease in electronegativity, also due to this decrease in electronegativity, the difference in energy between 5d and 6p orbitals would be very small, and therefore it can overlap to give a DP type of hybrid orbitals, which is actually very much suitable for pi back bonding with the ligands in type of TBB intermediate or transition state, through which actually they are showing trans effect. Or when actually we are comparing between platinum 2 and platinum 4 to show the trans effect, then we should consider the sigma effect or the ground state theory. Actually, in the ground state theory, actually whatever was happening, that among the symmetric ligands, whatever we have taken like eggs, one of the eggs actually is being replaced by L, where L is actually highly polarizing, then therefore it would try to pull the electron density towards itself, therefore it would induce, therefore the positive therefore the charge on the metal atom actually would induce and dipole to the side of L, or a dipole on L, and these may in turn induce a net polarization on the metal in a manner that it would repel the negative charge on the X, on the ligand X, which is actually trans to L. Therefore the X would be released easily. So now the basic theory is that when the L would be more polarizing, the metal should be actually highly polarizable. Actually the polarizability of the metal actually in turn favoring the high polarizing power of ligand, because this is actually favoring the condition, or this is actually favoring the trans effect. But if the metal would be less polarizable, then definitely the trans effect would be less, or the or the tendency to show the trans effect would be minimized. Now among platinum 2 and platinum 4, the charge of platinum 2 is quite less, whereas the size would be more, whereas in case of platinum 4, the charge is high and the radii would be less, so therefore it would be less polarizable in nature, and it would try to show very less trans effect. Okay, so now another question is that the 5 coordinate intermediate in square planar substitution might also have a square pyramid type of geometry. See that we are drawing only a TBP type of geometry, but instead of this we can draw this type of geometry, right? This is actually square pyramid, right? So see that whenever we are considering a 5 coordinate intermediate, so instead of a square planar substitute, instead of a TBP geometry, we can draw a square pyramid geometry also, because in that case actually it would have a higher CFSE, that is crystal field stabilizing energy. But actually what factors favor the TBP geometry? Because in case of TBP geometry, when this actually we will if we are going to draw this type of intermediate instead of TBP, where in case of TBP the ligands will repel to each other comparatively very less than in the case of square pyramid. Why? Because the basic bond angle difference between the ligands is 90 degree in square pyramid geometry in the plane, right? The ligands in the plane, they are actually in a bond angle which is 90 degree. Okay, the each ligand actually is maintaining a bond angle 90 degree to another one, so therefore they are more prone to show bond angle repulsion between them, whereas rather than the case in TBP geometry, where the bond angle between the ligands is actually 120 degree, so therefore they are involved in a very smaller repulsion. Okay, or you can say that in this TBP configuration, the ligands will repel to each other quite small in amount rather than the ligands placed in the square pyramid geometry. And you can say that as per the question, the square pyramid geometry is having the higher CFSE value, whereas in case of TBP geometry it is having a lower CFSE value. So why it is still preferring the low CFSE valued TBP geometry? Because in case of TBP geometry it is being stabilized by an additional stabilization factor, which is actually metal to ligand pi bonding. So therefore the loss in CFSE is compensated by greater pi bonding in TBP structure. In trigonal plane, two pi bonds can be formed simultaneously with any two of the equatorial ligands. So therefore, the loss in CFAC is being compensated due to this metal to ligand pi bonding, which in turn actually favoring the low CFAC valued TBP geometry or TBP structure over the square pyramid geometry. So now we are moving to some trans effect example. So far we have already learned what is trans effect, what is a trans effect order, what are the trans effects theory, what are the basic mechanisms regarding this trans effect, and how actually it is showing, or what kind of theory is basically responsible behind this. Now we are going through some examples. See, here we have shown the formation of cis and trans platinum NH2 whole to Cl2, where actually it is also called as cis-platin or trans-platin, right? It is called as cis-platin or trans-platin. Now, whenever we will move to have some examples regarding trans effect, basically we should remember three things. First one is that is bond strength. Next is trans effect, which actually we have already learned just now. And third one is the reaction condition. So basically three things we should keep in our mind to have some examples, to have some synthesis, to have some transformation through the trans effect. The three things are, first one is bond strength, second one is trans effect, and third one would be the reaction condition, because the three things would be applicable whenever we are going to synthesize anything through this trans effect mechanism, or you can say that through this trans effect topic. Now when we are transferring platinum NH3 whole for 2 plus to trans platin or platinum Cl4 2 minus to cisplatin, see that here in this case all are symmetric, all ligands are same, so therefore it is a symmetric structure and hence the trans effect cannot occur here. So now when chloride is attacking the square planar complex, so basically one ammonia is actually leaving, or one ammonia is being replaced by one chlorine. Now the trans effect order is Cl minus is greater than NH3. But in the first step actually we cannot show the trans effect. Why? Because in this case all NH3s are same, or these are having a symmetric structure, so therefore we cannot show here the trans effect. So how the reaction is occurring, or the which factor actually favoring the reaction, you have to mention that. You have, if you are not mentioning the factor which is favoring the step, that is from this to this, then definitely you will lose marks if you are going to ask this type of questions. So now when Cl minus is replacing one of the NH3, any one of the NH3, so basically this step is being preferred due to the reaction condition. Why we are taking this reaction condition into the picture? Because see that trans effect is not occurring here because of this symmetric nature of the complex. Second one is the bond strength. Now you have to remember this one also, that platinum nitrogen bond strength is more than platinum chlorine bond strength, and this bond strength is directly proportional to the electronegativity difference. So you can easily calculate the bond strength order, and the trans effect order you can either remember through the series, or you can just have an idea through the sigma effect and through the sigma donating nature, or through the pi accepting nature of the ligands, whichever we have already discussed in our last slides. Okay, so you have to remember the trans effect order, or you can just think of it through the mechanistic pathway or through the ideas of sigma donor and pi accepting character. And you have to remember the bond strength order also, or if you have a just a very basic idea regarding the electronegativity difference, then you can just understand the bond strength difference, or you can calculate the bond strength differences between these two bonds. So basically platinum nitrogen bond would be more strong than the platinum chlorine bond. But what actually we are getting here, that one platinum nitrogen bond is being broken, whereas one platinum chlorine bond is being actually made, or one platinum chlorine bond actually is being formed. So we are getting a weak bond and breaking a strong bond. So the bond strength is not preferring the step also. So therefore the last condition is, that is the reaction condition, is actually favoring the step. So when the trans effect would fail, when the bond strength would fail, so then definitely the third condition, that is the reaction condition, will come into the picture for the step. Okay, so you have to remember this, that first we will see about the trans effect. If trans effect is occurring, then we would say that the step is being favored through the trans effect. Second, we would consider the bond strength if the trans effect is not occurring there. Now if the bond strength is favoring the step, then it is okay, we will show that the bond strength is actually favoring the step. But if the bond strength is still not favoring, then the reaction condition would come into the picture. Now we are moving to the next step. Now in the next step, actually what we are doing, in the next step actually we are again actually eliminating, or we are again actually replacing one ammonia or one NH3 through Cl- ligand, right? Now if we are considering this NH2 which is being replaced, that is basically trans to this chlorine, right? Now trans effect of Cl- is greater than NH3. So this chlorine is actually try to release this NH3 through the trans effect. So now basically this is happening because this chlorine is coming in this place, or in the place of NH3. So basically this step is being favored through the trans effect. Why? Because this ammonia which is being actually released, that is completely trans to this chlorine, and the chlorine is having a greater trans effect than ammonia. So this chlorine is try to release this ammonia or to replace this ammonia due to its more trans effect than NH3 ligand. So therefore it will replace this NH3 ligand with one of the chlorine, and therefore the trans platinum would be formed. Okay, now in the last one, here we are considering the PtCl4 So when NH3 is coming, or NH3 is reacting with this, therefore here we cannot take trans effect as the favoring one, right? We cannot take the trans effect is favoring this step because of the symmetric nature of PtCl4 Now what is happening? We will then consider the bond strength. Now here one platinum nitrogen bond is being formed and platinum chlorine bond is being broken, right? That is, platinum nitrogen bond is being formed and platinum chlorine bond is being broken. So therefore we can directly say that due to this bond strength order, that is platinum nitrogen bond is more strong than platinum chlorine bond. So here actually a more strong bond is being formed and a less strong or a weak bond is broken. So therefore this is favoring, or you can say that the bond strength is favoring this step, right? If the bond strength was not favoring the step, then we can definitely say the reaction condition would favor the step. Okay, so we have already determined this step. Now in the next step, if we are going to add another ammonia and we just try to do this, then first we can take the example of trans effect. Now the trans effect of chlorine is more than ammonia. So if we are going to show the trans effect as the favoring factor here, then definitely this chlorine will try to release this ammonia, and again the same product would be formed, right? This product should be formed again, because this chlorine would just try to release this ammonia, and instead this ammonia would be added, right? But we are not trying to get that product, we are trying to get the cisplatin, right? But for the cisplatin, what actually we are trying to get means, what we are trying to do with this intermediate, that is this platinum chlorine bond or this platinum chlorine bond should be broken, and instead of that bond actually one platinum nitrogen bond should be formed. But here you can see that two chlorines are completely trans to each other, therefore they are not going to show any kind of trans effect because of the symmetric nature, right? But you can think about the bond strength, because instead of this one platinum chlorine bond or this platinum chlorine bond, the platinum nitrogen bond is going to be formed, which is even more strong than the platinum chlorine bond. So therefore here again the bond strength is playing the role. Okay, so see, for any kind of synthesis or any kind of transformation, the three things you have to remember. First one would be the bond strength. The bond strength order you can easily calculate through the idea of electronegativity difference. Second one would be the trans effect. The trans effect order even you can easily memorize through the series, or you can have an idea, if you have an idea regarding the sigma donor character or pi acceptance character of different type of ligands, then you can easily understand the order or understand the series of trans affecting ligands. And the third one is the reaction condition. So first you have to follow the trans effect. If the trans effect is favoring any kind of step, then you have to mention that the trans effect is favoring that step. And the second one would be the bond strength. If the trans effect is not favoring the step, or you cannot show the trans effect in that step, then you should consider the bond strength. Why? If the bond strength is actually favoring the step, or if the bond strength is coming into the picture, then it is okay. But if again the bond strength is not coming into the picture, then the third thing, that is the reaction condition, is in your hand, and you have to show the reaction condition in the step, because it is actually now preferring the, or it is actually now favoring the step. Okay, now we'll again move to another example. So here you are going to prepare cis and trans platinum NH3NO2Cl2. Okay, so here now again the structure is symmetric, here also the structure is symmetric. So now the trans effect will not play the role in the first step. So when ammonia is going to be added, definitely we will consider either the bond strength or reaction condition. So now here one platinum chlorine bond is being broken and the platinum nitrogen bond is being formed. So here the weak bond is broken and the strong bond is being formed. So therefore the bond strength is actually favoring this step. Now in the second step, now we are considering the trans effect. Now so now if we are considering the trans effect, then see that these two chlorines are trans to each other, then therefore they are not going to show any kind of trans effect. Now these chlorine have an trans effect with this NH3 because it is trans to NH3. Now the trans effect of chlorine is more than NH3, so then definitely when it is reacted to NO2, if the step is being favored by the trans effect, then this NH3 should have been replaced by this NO2 minus. But we don't want to get that, because we just need to incorporate one ammonia and one NO2, right? So at least two chlorine should be replaced and one ammonia and one NO2 should be added in the system. So now therefore this thing should not come into the picture. So we should consider these two chlorines. Now when we are considering these two chlorines, definitely trans effect would not come into the picture. Why? Because the chlorines which are trans to each other actually symmetric in nature, therefore they are not going to show any kind of trans effect. So now when NO2 is being added, again one platinum chlorine bond, either this bond or either this bond would be broken, and instead of this one platinum nitrogen bond would be formed. So therefore again the bond strength is preferring, or the bond strength is actually playing the role for this step also. And you have to show this kind of thing, because whenever you are going to perform any kind of synthesis, or whenever you have been asked to transform any kind of reagent to product, then definitely in each step you have to show the role, or you have to show the factor which is actually responsible for any kind of step. So we are now moving to our next reaction, that when these platinum Cl4 2- are being reacted with NO2 minus. Okay, so now again one platinum chlorine bond is broken and platinum nitrogen bond is being formed, and platinum nitrogen bond being a stronger one, so the bond strength is preferring the step. Now in the next case, when we are adding NH3 actually, or if say for example just we considering the trans effect for the first again for the first time. So now in this case, these for these two chlorine trans effect will not play a role, but in this case actually trans effect will play a role, and now the trans effect of NO2 is greater than this chlorine, right? Now if you are adding any kind of ligand, this NO2 will replace this Cl minus and will put the attacking ligand here, right? So now if NH3 is being reacted, so due to the trans effect actually NH3 should come here, right? So we can say that the main factor in this step would be the trans effect, or trans effect will play, or the trans effect is playing the main role for this step. Okay, wherever in the first reaction both the steps are being favored through the bond strength, wherever in the last case the first step is being preferred through the bond strength, whereas the last step would be preferred through the trans effect. লাস্ট একটা জিনিস একটুখানি বলা দরকার, সেটা হচ্ছে যখনই এই ধরনের কোনো প্রবলেম পড়বে, ফর এক্সাম্পল তোমাদের কোনো সিনথেসিস করতে দিচ্ছে অথবা ট্রান্সফরমেশন করতে দিচ্ছে, ট্রান্সফরমেশন আইডিয়াটা প্রথমে আমার মাথায় আনা উচিত। ফর এক্সাম্পল এখানে দেখো দুটোই আমরা PtCl4 2- থেকে শুরু করেছি এবং আমাকে বলেছে সিজ এন্ড ট্রান্স পিটি NH3 আর NO2 এই দুটো লিগ্যান্ডকে আনতে, মানে কি দুটো ক্লোরিন বের হচ্ছে এবং দুটো ক্লোরিনের জায়গায় উই আর পুটিং ওয়ান NH3 and another one ligand would be the NO2. So now basically from the first step or through this structure of the complex we cannot come into the picture that how will you do that. It is basically a trial and error method, right? আমরা প্রথমে কি করছি, যে কোনো একটা লিগ্যান্ডকে নিয়ে কাজ করছি। ফর এক্সাম্পল আমরা প্রথম স্টেপটা করেছি NH3 কে নিয়ে, তোমরা প্রথম স্টেপটাকে NO2 কে নিয়েও কাজ করতে পারো। যখনই NH3 কে নিয়ে কাজ করছি একটা ক্লোরিনের বদলে আমরা অ্যামোনিয়া ঢোকালাম, কারণ এটা হচ্ছে আমার বন্ড স্ট্রেংথের অর্ডার। এরপরে আমরা দেখছি একটা NO2 কে ঢোকাতে হবে। যদি NO2 টাকে আমি ঢোকাতে যাই থ্রু ট্রান্স এফেক্ট, it is not possible because if we are just putting the trans effect in this manner then definitely this chlorine actually will replace the ammonia and we are not trying to do that. তাহলে অ্যাকচুয়ালি থ্রু বন্ড স্ট্রেংথ আমরা অ্যাকচুয়ালি এটাকে ঢোকাতে পারি, আর থ্রু বন্ড স্ট্রেংথ যদি ঢোকাই তাহলে আমরা তখন বলতে পারি যে এইখানে অ্যাকচুয়ালি সেটা ঢুকবে, কারণ থ্রু বন্ড স্ট্রেংথ যদি দেখাতে হয় তাহলে আমার সেটা সিজে দেখাতে হবে, কারণ আমি এখানে আমি কখনোই ঢোকাতে পারবো না। ওকে, এবার আমরা বলছি PtCl4 2- থেকে আবার প্রথমে NO2- দিলাম। তাহলে NO2- যখন আমরা দিচ্ছি তাহলে যে কোনো একটা ক্লোরিন বের হচ্ছে এবং NO2 ঢুকছে, এটা ডিউ টু বন্ড স্ট্রেংথ। নাও এবারে ট্রান্স এফেক্ট সেখানে আসছে কি আসছে না, না এখানে ট্রান্স এফেক্ট রোলটা কিন্তু প্লে করছে, কারণ NO2- ইজ হ্যাভিং আ গ্রেটার ট্রান্স এফেক্ট দ্যান Cl-। তাহলে এখানে ট্রান্স এফেক্টের থ্রুতে আমরা অ্যামোনিয়াটাকে ঢোকাতে পারছি বিকজ অফ দিস গ্রেটার ট্রান্স এফেক্ট অর্ডার অফ NO2- and it would give a trans product also, that is trans platinum NH3NO2 Cl2. okay, তাহলে এইগুলো জিনিস এই কিছু জিনিস তোমাদের মনে রাখতে হবে। Now we are moving to our next example. okay, so here we have also shown a different type of things that when PtCl4 2- is being attacked with this NH3, definitely this step would be the bond strength. Definitely whenever we are being attacked with pyridine, it would also be the bond strength. Now when this is attacked with 2-pyridine, definitely it would be the bond strength. okay, so now we are considering the next step. Now when we are considering the next step, it is being attacked with Br-. Now when it is being attacked with Br-, first you have to consider the trans effect. Now the trans effect order you have to show that Br- is having a greater trans effect than Cl, than pyridine, than NH3. Now Cl- is having a greater trans effect than NH3. So when Br- is being attacked, so definitely if we are considering the trans effect, this chlorine will replace this ammonia with bromide. So we are not going to we are not trying to get that. We are trying to replace the other Cl-, right? Because we are just substitute the other Cl chlorides. So now if we are just try to replace these chlorides, definitely the trans effect would not come into the picture because of the symmetric nature. Now we have to think about the bond strength then. So now the bond strength is that platinum bromine bond is having a greater bond strength than platinum chlorine bond. So definitely one platinum bromine bond is being formed instead of this platinum chlorine bond. Definitely bond strength will come into the picture. Now we are going to add the pyridine. So now if we are going to add the pyridine, first of all we have to try to think about the trans effect. So now the trans effect order is, that is bromine greater than chlorine greater than pyridine greater than ammonia. So now bromine is there, right? So now when bromine is there, this bromine is having a greater trans effect. This bromine is having a greater trans effect than chlorine. So now this bromine can replace this chlorine. So now through this trans effect we can replace this chlorine with pyridine, and we are getting this, right? So similar would be these examples with these trans effect, bond strength, and reaction condition. You can note down these examples and try as like your homework. You can just try to do it separately in your as your assignment, and each step has to be mentioned. Either it would be the trans effect, or it would be the bond strength, or it would be the reaction condition. And I am summarizing once again that whenever it would be a synthesis or a transition or a transformation case, or means from reaction to product transformation, definitely you have to first consider the trans effect. If it is possible there, then it is okay, and you have to mention that. Next, if it is not being operated there, you have to consider the bond strength thing, or the bond strength purpose. If the bond strength is okay, if the bond strength is occurring, then it is okay. But if the bond strength is not coming into the picture, then you have to just consider the reaction condition. And with the help of these three things, that is the bond strength, trans effect, and reaction condition, you have to draw the overall transformation. Okay, just you can take these two reactions as your homework and do it as per I have told, that in each step you have to show either it would be bond strength or trans effect or the reaction condition. So we are just moving to our next slide, that is one kind of trans effect application. Sometimes see that it is the one of question that explain the following observations. The first case, that whenever you are using thiourea, when in the first case you are using this thiourea, so now this thiourea is being attached here, right? So we are just adding thiourea, or we are replacing one Cl minus, and we're adding thiourea. But we know that trans effect of chloride is more than ammonia. So basically this would not be the trans effect step, right? Whereas when you are adding one thiourea again, or thiourea slight excesses, then again the other bond, or sorry not this bond, means when, in the next step, actually here actually two steps are generally written in one in only one step, means two individual addition of thiourea has been shown in one step. Means here actually two thiourea has been added. So basically these are being replaced, these two chlorines. But when actually we are adding more thiourea, basically nothing would be added. Why? Because see, the when we are actually adding more thiourea, basically the other ammonia is being replaced, means that all over would be the thiourea. So basically I am just summarizing once again that when this we are adding thiourea here, so basically this is the two thiourea unit, or when two thiourea units are being added with this complex, so basically these chlorine bonds or these chlorines are being replaced with thiourea. Now the trans effect of Cl minus, the trans effect of Cl minus is more than ammonia. So basically the first step would be the not the trans effect. This is not the trans effect. So this would be the either bond strength or the reaction condition as per your knowledge you can put here. So now when the again the thiourea would be used, then what is happening? See that when again we are using the thiourea, now the trans effect of thiourea is more than ammonia, right? The trans effect of thiourea is more than ammonia. Now this thiourea can replace this ammonia, and or this thiourea can replace this ammonia. So therefore all ammonia or all positions will be occupied by the thiourea. Whereas in case of trans isomer, when one thiourea is being added or two thioureas are being added, they would occupy these two chlorine position. Because of this not trans effect either bond strength or the reaction condition. But when excess thiourea would be used, but now in the trans position both are thioureas, whereas in this case in the trans position both are ammonia. So basically there would not be any kind of trans effect, and here nothing or not a single molecule of thiourea would react again, or it would react, the trans isomer would react only with 2 moles of thioureas, whereas in case of cis isomer it is reacting with 4 moles of thioureas, right? Or in other words you can say that after addition of 2 moles of thioureas to each, the cis isomer is still reacting with excess thiourea, whereas the trans isomer would not react afterwards. Okay, so this is basically another example with these trans platinum and cisplatin, and this can come as a question that how can we distinguish between cis and trans platin. So whenever this type of question is coming, so basically you can just draw this kind of reactions, or you can show the thing as per these as per the transformations, that whenever we are using or whenever we are going to react these cis and trans platin with thiourea, the cis platin and trans platin after reacting 2 moles of thioureas, they will form a complex, whether the cis platin even after addition of again thiourea it will react, but trans platin will not react, because in case of cis platin the stronger trans effect of thiourea actually levelizes both ammonia, like in this case actually the strong trans effect of thiourea actually levelizes both ammonia, and therefore the all positions are being occupied by thiourea, whereas in case of trans platin after the first addition of thiourea, that is 2 moles of thiourea, now the trans positions are being occupied with similar ligands, like 2 NH3 are trans to each other, whereas 2 thioureas are opposite to each other, therefore they cannot show the trans effect. So here when thiourea are being added, definitely it would not react further, therefore we are not getting here any kind of reaction, whereas it would be a yellow colored, solid, that is platinum complex with 4 thiourea ligands. Okay, so basically this can come as a question that how to distinguish or how to differentiate between cisplatin and transplatin. So you have to show this by these 2 reactions with a shorter explanation, that is strong trans effect of thiourea greatly levelizes both ammonia, and it would be a yellow colored complex, where in the next latter case, that is in case of a transplatin, it would not give any kind of colored complex. Okay, so I think that so far we have learned the things like trans effect, what is trans effect, what are the trans affecting order, that is a series of trans effect ligands, and there are the 2 theories of trans effect, that is a ground state effect or sigma effect, another one is the transition state effect or the pi effect. The mechanism of these type of theories, the pathways of this type of theories, which pathways are favored and why, and how this is actually happening, and after that through this theory we have taken some examples and some applications also. Okay, so I think so far so good. And finally I want to mention that in this case, that is the reactions between cis and transplatin, and the distinguish, that is the process to distinguish this thing. That is the first reaction, that is the reaction which is named as A, is basically named as Kurnikov test. It's basically named as Kurnikov test. So actually it is important when you are going to be asked how to distinguish between cis and transplatin, so you have to answer like this, that through the Kurnikov test actually we can distinguish, because of the cisplatin will react like this, or the transplatin will react like this. The cisplatin actually will form a yellow colored needle type of solution or complex formation, whereas in case of transplatin nothing will be formed. Means that the cis isomer can form either a yellow solution or it can give a yellow precipitate also, or in other words the cis isomer actually after addition with 2 thiourea it would further react when thiourea are used in excess, whereas in case of trans isomer after addition of 2 thiourea units actually it would not react with further with excess if excess of thiourea is used. And the second thing, that is the second reaction, can also be used in case of to distinguish between cis and transplatin, but it is actually less preferable, and the first thing, that is the Kurnikov test, is more preferable than this. So far so good. I think that we have learned enough in today's class. We have learned the trans effect and different significances related to the trans effect also, and I hope that you have understood the things properly, as we have discussed in deep also the things, and whatever I tried my best. And just please try to read this thing properly. I will provide the study notes as means whenever I will if I am going to be managed quite in a short period of time, I will definitely provide to you. And till the time, just try to read it. And thank you for watching this video. Have a good day.